Hello. Yeah. Can you hear me now, Amandeep?
Hello.
Yes.
Yes, ma'am, I can hear you now.
Okay. You can send the link to the class. But what I'll do is I'll make you co-host. I think I was trying to see if I can admit people without having to press OK every time. But I don't know. I didn't get those settings. So I'll make you co-host. I'll make you host as well. No, but you want to change the host to Amandeep. So you can admit. Okay.
Okay, ma'am.
The meeting password is 12345. Somebody needs it.
Okay, okay, ma'am.
Okay, just
Ma'am,
send.
shall I send the link?
Yeah, send the link now. Meet is easier, but this has a whiteboard, so this will be useful.
Ma'am, your audio is, very less.
Just a second. I don't know. I tried yesterday as well with somebody. It was working fine. Let me see. Is it that very bad, or do I need to
Ma'am,
speak?
it's okay.
It's okay.
It's okay now. It's okay. Yes,
Okay,
ma'am. Yes,
fine. Okay, you have to. Okay, Amandeep, once everybody is there, you have to make me the host because I'm not able to share my screen.
Okay, okay, ma'am.
Uh, I guess we should start. I think almost half the class is there.
Ma'am, you are the host now.
Okay, fine. Thank you. Okay, let's see. It's 29. Okay, so let me start. Today's class is going to be just an introductory class. We will, I'm admitting as participants are coming in, so don't worry about that. So, just a second. Okay, so let's start. So, this course is a continuation of your data structures in a way that you have now studied different data structures, and now you should be able to decide which data structure you have to use in a program based on the pros and cons of the data structure that are known to you. So you are in a better position to decide if you're writing a program, what kind of data you have, what kind of data structure will be most efficient. Okay. So what we are going to do in this course is essentially we are not designing algorithms. It is more of studying the already standard designed algorithms and studying how we define whether an algorithm is good or bad, efficient or not efficient. So we'll be going over that. So, okay, so we'll go over the brief history of how algorithms actually came into place. And then we'll see what do we mean by design and what is analysis. Analysis of algorithms is basically your speed at which your program runs and how much space it takes. We call it time and space complexity. Then how do you analyze a program? Basically, if you've written some code, you want to know how efficient it is compared to the same uh, program that has been implemented by somebody else using a different method. So you should be able to figure out which one is better, yours or that person's. And we'll see what are the different types of algorithms that we will study over the course of this program. Okay. So the word algorithm itself is actually, it has come from the name of he was a mathematician. His name was Musa al-Khwarizmi. His work was converted or translated into Latin first, and from there his name Khwarizmi is what is actually, it was named algorithmy when it was translated. And then finally the Latin word algorithm came into picture, and now it's used in English to describe algorithms. So he wrote a book. The name of the book is quite long, Al Kitab al Mukhtasar fi Hisab al Jabr. Jabr is actually the word from where algebra has come. So it is a compendious book on calculation by completion and balancing. It was written in 825 AD. And Jabr, Al-Jabra, if you've heard, Al-Jabra ne Jabr kiya to kalam bichara kya kare. So the Jabr is from the word from where algebra has come. So he lived in the 9th century. It was known as the Islamic Golden Age. And he introduced, he did a lot of work on algebra. And there's some more details, you can go through it. And what we are concerned about is the algorithm or algorithm. This is named after him. The Khwarizmi is actually the word algorithm. So he has also worked with zero and Arabic numerals that we know of now. And it is his work that was later converted into Latin. So the Latin algorithmy is the English algorithm that we know now. Okay. So what is algorithm? You have already written algorithms to even write your basic C programs, and then you've written algorithms to implement your data structures. So what algorithm is just a sequence of steps that you follow to solve a particular problem. Two different people solving the same problem can use two different approaches. So if you remember our last topic in data structures was sorting. So you saw there were, let's say, 7, 8 sorting algorithms that we discussed. All of them did the same thing. All of them sorted sorted arrays, for example. But then the methods used in all of them were different. So there were different algorithms solving the same sorting problem. Okay, so there are various definitions you'll see. The first one that you see is a detailed definition. It is a well-defined computational procedure that takes some value, set of values as input, or it produces some value or set of values as output. And just to solve a certain problem means that you are applying some kind of algorithm in it. So if you see Google and you see the first definition that comes there is the set of rules or procedures that you follow to solve or calculate any problem, especially by a computer. That's where this word algorithm is used. It is a finite list of instructions that you give and you expect an output which is correct. So when you're writing an algorithm, the first thing is that your algorithm should be correct. Correct in the sense it is giving you the output that you actually started. You started with the problem and you need an output. The output should be correct. Okay. Then once it is correct, then we come to the point of discussing whether this algorithm is good, bad, efficient. You can compare it with something else only when your output is the correct output that you actually desired at the beginning. Okay. So what we have to do is whenever you have to write a program, you should know what is the input to your program and what is expected as an output. And in between the whole program that you have to write is actually the algorithm that you have to write. So you have to design, first of all, if you are getting an input from a user or a file or from anywhere else, you have to decide, first of all, where to put it. So the first thing is you will decide which data structure to put it in. Now, the data structure you put it in has its own advantages and disadvantages. So you should know what you are going to do with the data so that you can decide which data structure would be more efficient in dealing with this particular data. Okay. Then based on the data structure, then you will You'll first decide how to solve the problem. That will involve deciding which data structure to choose, and then what steps to follow to get the correct output. And then once you are done and you get a correct output, so correct output is important, then you sit down and see, let's see how good my procedure or my design of this whole program is, which is basically how good your algorithm is. So you have to sit down and analyze your algorithm. And how do you analyze your algorithm? There are many things you have to see. First of all, uh, if you see the definition here, it says predict the cost of an algorithm in terms of resources and performance. Performance, normally we think of performance as time. How long does it take if you give an input to the computer? How long does it take for you to give an output? Let's say a click on a web page, and how long does it take to load the next page? So that is timing, performance with respect to time. Performance with respect to resources, how can you solve a problem? By consuming the minimum resources. Nowadays, space is not an issue. Earlier days, RAM was limited, so you had to think of resources in terms of space as well. So what are resources? Resources can mean space. Sometimes it can also mean how many processors are available to do the job when you're talking of parallel algorithms and all. Performance means how fast, how quickly you're getting. So what is the cost of your algorithm? It will be a combination of the time and space it takes, pro- provided your algorithm is correct. Correct in the sense it is giving you the correct output. So how much time and space does an algorithm take to run and give you results? So basically that is the cost that we look at. So nowadays space is not that much of an issue, like I said. So mostly it is the timing analysis of the program. So we want correct results. We want correct results to be given to us efficiently, making the best use of time and space. Okay. So time, what is time? If you, I think you are taking a, what is that, architecture course this semester. So you will see how you've done microprocessors already. So you will actually go down to the basics of how gates are used to do your basic additions, deletions, multiplications inside your computer. So you'll see we talk of cycles. There are time slices given and how many clock cycles it takes. So all that accounts to the time it takes to do a particular thing or a particular step of an instruction given to the computer. Okay. So when we are analyzing, we don't go down to that level of the gate design and clock cycles. We do it at a higher level. You'll see in a while. So we count how much time an instruction takes. For example, your instruction in a C program can be, let's say, a simple increment operator, x plus plus. So x is equal to x plus 1. So how much time does it take to execute? So a lot of those, that time will also depend on what type of system you're working. So considering we are working on an average system where things like addition, deletions take same time, what we are looking at is when we write a program, how do our instructions or how does our way of writing the program actually affect the time taken to execute the entire program. Okay, so how fast does the algorithm perform? Normally we do it in comparison with some other program, or we do it in comparison with a mathematical function. I'll just explain that in a while. What affects its runtime? Sometimes the input given to a particular program affects the runtime. For example, if I give you a sorted input and I ask you to I ask you to write a bubble sort. If you remember, we had a check inside the bubble sort loop where we would check if there are no swaps that take place in a particular cycle, then we stop, we exit the loop. So if you're already given an input, the runtime of bubble sort will be affected. obviously it will be lesser if it's a sorted input. If it's not a sorted input, it's totally, let's say, the opposite order. You want to do ascending, it is descending. It will take almost the complete cycle of the for loop in the bubble sort. So your type of input also affects the runtime of your program. It can make it good or it can make it bad. But when we talk of the time a particular program or an algorithm takes to run, we do not consider the best case, because you cannot give assurance to somebody that I've written this program, this is the best runtime. Just give me a second, just hold on. Okay. uh, yeah, sorry, I had to set up class for my own daughter on my phone. Okay, so like I said, uh, your type of input also determines the time it takes to run a program. Okay, and when we, like I was talking about the best and the worst case performance. So uh, whenever you, as a programmer, whenever you tell somebody about the efficiency of your program, best case should not be considered, because based on your input and the situation, the conditions in which your program runs, you have to tell your possible client that this is the worst case runtime. That my runtime, I'm assuring you, it will not go beyond, let's say, a program, the maximum time it will take to run for given on a particular input is, let's say, 10 seconds. Maybe your program also runs in 1 second, but you cannot tell him that my program runs in 1 second. That is your best case scenario. You do not give your best case scenario, you give your worst case. It is like telling, this is the best time reduction that I have done. I'm giving you 10-second worst case time. So whenever we talk of time analysis, we'll be giving the worst case scenario. Worst doesn't mean that your program is bad. It means that this is the worst waiting time, or let's say a running time of my program. It will not go beyond that. So that is the assurance that you give. So we'll see that in a while. Then space, your data, like I said, data structures take space. We have discussed how linked lists are better or arrays are better, why we use linked list, why we use arrays. So you have to see what kind of input you are given in a program, what kind of work you're supposed to be doing. Lot of insertions and deletions, avoid using arrays, use linked list. Very few insertions and deletions, then use arrays, because then it'll be easier access. Maybe accessing is more. For example, when you make hash tables, okay, if you choose a very small size of the hash table, you'll have clashes and you'll have to go for collision resolution. If you have a lot of space available, go for a big table and have a single access and write a hash function, so that you don't have to worry about collisions and collision resolution, because that also takes time when something like that is happening at the background of your program. So see what data structure you need. Just give me a second. Close the door. Okay, sorry. So data structures, you decide what data structure will be the best for your program. Remind yourself of the pros and cons. See what your program is going to do. See how much data you're expecting, and how the choice of your data structure can affect the runtime of the program. So very often nowadays we can trade, like I said, space for time. Like I gave you the example of a hash table. You can choose a big size hash table so that you avoid collisions, and you have better direct access to elements so that you can access elements faster without having to go through chaining and all that procedure, or rehashing or double hashing and all that stuff to store and retrieve your data. So you have to find the right balance. So to be a good programmer, you should be able to choose a good data structure, and you should be able to use efficient method on these data structures so that you can have a good runtime for an algorithm. Okay. So how do you calculate the, now we're talking about time complexity, as in how much time a program takes to run. Okay. So for simplicity, we assume that if you have a single statement, let's say if you're doing a logical comparison, a is less than b, or you're doing an increment a plus plus, okay, a single a single statement of your code, which involves, let's say, an addition or a deletion or something like that, a single statement of your program runs in, let's say, constant time 1. Okay. I'll not talk about this O of 1. We'll come to that in the next class probably. So you can just say, instead of reading it as O of 1 right now, just read it as that one step or one line of your program takes, let's say, 1 unit of time, whatever your unit of time is. Okay. Now, if you go to the second uh, point here, single loop. If your program has a single loop, what does a single loop mean? A particular statement is repeated n number of times. N is the size or the loop, maximum size of the loop. So I runs from 1 to n, and you have, let's say, a plus plus inside this loop. So this loop, based on I, let's say if my for loop had something else inside which was changing I, so the loop could end before uh, actually executing n number of times. But in this case, it will obviously execute n number of times. What I have inside the loop is a plus plus, which is a single statement. I can take it as 1 unit of time. This 1 unit of time is run n times because the loop size is n. So my runtime for this, if my program has just this loop, it is going to be again O of n. So forget about this O as of now. You can just read it as a function of n. So my program will run the statement n times. So if you take 1 unit of time to execute one statement, you will take n units of time. Okay. Now, if instead of a single loop, I have a nested loop. So what happens in a nested loop? You remember in your bubble sort, you have a double for loop. So I don't know, many of you did tell me during your Viva, the complexity is n square. So what do we mean by that? Again, if the same statement a plus plus is within a double for loop, one of the for loop runs from 1 to n, the other one also runs from 1 to n. So the number of times a plus plus is going to run is n into n, which is n square. So if a plus plus doing that takes 1 unit of time, doing that within a double for loop takes n square units of time. So we mathematically, we say it's a function of n square. So what this O is also a function. We'll talk about it later. So in a program, you can have simple statements, you can have for loops, you can have double for loops, you can have consecutive loops or consecutive statements. So you have a single for loop followed by a double for loop, or you have a single for loop followed by another single for loop, or you just have set of statements following each other. So what we do in that case, we add them up all together. So if you see in this example here, There is a for loop that runs for from I is equal to 1 to m. There's another for loop following it where I goes from 1 to n. So first loop will take m number of m units of time, second loop will take n units of time. So for consecutive loops, consecutive statements, you'll just add the time. So time, m units of time and n units of time. Okay, so that is O of m plus O of n. Again, O is a function of m and a function of n. You'll get to know about it later. And which is total of O m plus n. If your m is equal to n, the time complexity becomes 2 of n, which is O of n. Again, why is 2 of O of 2n equal to O of n? We'll get to that later. So don't worry about it now. Then if you have a if else statement, so if you look at the example that I've given below, if of whatever, the statement inside runs for O of n, else the statement, whatever is inside the else block has O of n square time, runtime, okay? It can go into the if, it can go into the else, you don't know. So as a programmer, when you have to read your program to analyze it for time complexity, you will take the worst case. So worst is it can go into else and it can go into else and run n square times. Okay, yeah, just a second. Mute this. Okay, am I audible? Yeah. So when you have if else statements, you will take the worst case because your program can go either in the if block or in the else block. You have to give assurance. Your assurance for the program will be that it will worst case take on square. It can also run in on time, which is the best case. So you'll not give the best case assurance, you'll give the worst case assurance. Okay. Then you will also have programs where you use recursion. So till now 1 to 5 were things where iteration is used, so you can visually see what is happening. But when you talk of recursion, you don't know what is happening in the recursive program when you reach the base case and when you exit. Okay, so for calculating the time complexity of recursive functions, we write it down in the form of a mathematical recurrence relation, and then we calculate the complexity by solving that mathematical equation. So this is one separate topic which we'll take later. So what you need to understand is that if you see a recurrence or if you see recursion in your program, for example, your Fibonacci series, you know what is the recurrence relation for that, right? So that is what we take as the basis, and that is our recurrence relation, and that is what we will solve to find mathematically what mathematical function it follows, in the sense, uh, for example, if you have a for loop, it runs worst case for n units of time. So it grows linearly. If your n is 100, it will run 100 times. If your n is 1000, it will run for 1000 units of time. So as n increases, you have a linear increase. But in case of recurrence relation, it is different. So this time complexity for recursive functions will be dealt with separately. Okay, rest all you can just see what kind of statements are there in your program: if else, consecutive loops, consecutive statements, nested loops, single loop, single statement. So you can just scan your program and just find out the approximate runtime, because we're talking of giving 1 unit of time per statement. For example, I just have a simple increment here, a plus plus. It is a is equal to a plus 1. You can have a complicated mathematical equation, a is equal to a into b plus c divided by xyz, whatever. So that means you're including a lot more mathematical functions. And you'll see in your architecture program that you see multiplication is repeated addition and division is repeated subtraction. So all of that takes time. Okay. So these things are simple. And then this one, recursive functions will be taken care of separately. Okay. So basically, when you talk of algorithms, in this course, we are going to study algorithms. We are going to do a runtime analysis of known algorithms so that you can learn when you design an algorithm of your own, how you can do the runtime analysis. So runtime analysis is basically knowing how long it takes for your program to run. So you have to give an assurance of the maximum time it will take to run, which we call the worst case time complexity. How do you do runtime analysis? You follow the 1 to 5 steps we just did, and sixth one we'll do later on. Then for recursive programs, there are many methods defined, so we'll do them later. Okay. Then you should also know what is the efficiency of the algorithm. How do you define efficiency of the algorithm? You define by the runtime. How do you define the runtime? You evaluate your program, look for loops. Uh, Basically, we see where our program spends most of its time when it's executing. So if your program has a double for loop, definitely it is going to be there most of the time of its execution. Okay. If your program has a recursive call, obviously those recursive calls are going to take the majority of the time. So when we do runtime analysis, we we look at the part of the program or that code in the program which takes the maximum amount of time. And in a way, we say this is what will determine how long my program is going to be in the for loop, is what will determine its runtime. So you can ignore all the other small statements here and there, and you can just concentrate on that part which takes most of the time. Okay, so I gave you the example of sorting algorithms. So sorting algorithms, you have many algorithms given to you. If you can go back to your data structure notes and open all those for which we did the programs, you will see in merge sort, quick sort, you will see recursive calls. In bubble sort, insertion sort, you'll see uh, for loops. So you can just open those programs and see what is the runtime of those programs in terms of the 1 to 5 steps that we did. You can leave out the recursive for the while, but you can do the runtime analysis of your other sorting algorithms that we did. Okay, so these are the list that you see on the system on your screens right now. These are the basic, or you can say the main algorithms that we are going to study in this course. You have for each algorithm, we'll do a couple of examples, and then we'll study those examples. We'll do them completely, either pseudocode or proper code, and then with input output with working mathematical examples so that you can understand what is happening. And then we'll also do the runtime analysis of these algorithms. These are basic standard algorithms. There are many more approximate algorithms, parallel algorithms. Now we have genetic algorithms. So in your BTech course, these are the main algorithms that we study in detail. So for now, I'll just go over these, and we are going to take each one of them one by one, so except for brute force. So what is brute force algorithm? You're given a program and you do it, let's say in the worst, not in the worst possible way. You try all the methods, and then you just see which method gives you the result that is desired. So that is called a brute force. For example, a very simple real life example is making tea. Okay. If I have to make tea, I might have a different method of doing it. For example, I might boil the tea leaves with water separately first, then I'll put the milk, then I'll put the sugar. Another person might just use a tea bag, put it in the cup, pour some hot water, and pour some milk and sugar, and the tea is done. So another person, brute force would be he'll put everything in the you can say the vessel in on the gas, and put tea, sugar, leaves, whatever, milk and water, everything together, and let it boil, and the end result itself is tea. So that's a brute force in the sense he knows what all goes in the tea, he'll put everything together, and he'll obviously end up with tea. The tastes will differ, but then that is kind of brute force. You know what the ingredients are, you just put them in, and you'll get something which will be basically a different version of tea than what somebody expects using a tea bag, or boiling things separately, or having separate tea, or having masala chai, or whatever. They're different versions. Okay. So for example, a mathematical example of brute force would be, uh, let's say, even sorting. For example, you can I give you an array of 5 elements and I ask you to sort. What you do is you take this array or these set of numbers as a set. You find all the possible permutations or combinations of these 5 numbers. Obviously, one of those permutations, combinations will be the sorted order of this. And you say, oh, see, let's say I made so many permutations, combinations, and uh, number 5 is the sorted one. Okay. So that is a brute force approach. So you're not using any sorting algorithm to sort your program. You're just uh, rearranging all the elements in all the ways possible, and one of them obviously is going to be the sorted order. So that is your brute force. Simple recursive algorithms, many problems are inherently recursive. Like I said, in many problems, let's say if you see the Fibonacci series, the equation itself has a recursive nature. So inherently it is recursive, and that's the best way of solving them. So they are simple recursive problems. Then you have divide and conquer algorithms, where the whole point of divide and conquer, which you've already done in merge sort and quick sort, is that the belief is that if you divide the problem into its simpler counterparts, you will be able to solve the simpler problems, and then you combine the simpler solutions into the uh, solution for the actual problem. Okay. So similarly, you have dynamic programming algorithms. We're going to do all of them in detail. I'm just giving you an overview. In dynamic programming, what you do is, let me show you by an example. So let's see if I can write. Okay. So this is your Fibonacci series. Fib of n is n, fib of n minus 1 plus n minus 2. So when you are actually writing a program, you're calling two recursive functions, fib of n minus 1 and fib of n minus 2, which will be further n minus 2, n minus 3. This will be Okay, so if you see, there are repetitions in the recursive branching. Okay, so you have fib n minus 2 calculated here. You also have it calculated in another recursive call. So you're basically wasting your resources calculating something which you already calculated. You calculated fib n minus 2 here. Let's say we reached this branch first in calculation. And then you're doing the same calculation again on this side, which is a waste of your resources. So what we do in dynamic programming, we calculate the values and we store them in a table. And whenever we need them again, we use them from the table. So that is what your dynamic programming does. Okay. So uh, that is your dynamic programming in algorithms. So there are different examples of that. One of them is matrix multiplication, which we'll be covering. Then you have greedy algorithms. So as the name suggests, greedy algorithm is the one in which you use a greedy approach. Greedy approach means that if you, let's say you're looking at a problem where you want to maximize your profit, and it's not a one-step problem, it'll take multiple steps to solve that problem. So what you do is you are greedy and you select that option which gives you the maximum profit at the first place. And already previous example that you've already done of greedy algorithm is Kruskal's algorithm. So what you do in Kruskal's algorithm, you have to find the minimum spanning tree. So your aim is to minimize the cost of the spanning tree. Okay. So how do you minimize the cost of the spanning tree? In Kruskal's algorithm, you arrange all the edges in the ascending order of their weights, and you select the weight which is least first, and then you select the next weight which is the second least, making sure you do not make a cycle, so that you have to take care. But then you are being greedy at each step. You're not selecting the adjacent vertex or edge of a particular node. You are selecting the next least edge which seems the best to you at a particular point of time. Okay, so that is an example of a greedy algorithm. Graph algorithm, you already know, you've done Prim's Kruskal's. There are many others: Dijkstra's traveling salesman problem, finding shortest path from a particular node to all other nodes, finding shortest paths between all adjacent nodes. So a lot of these graph algorithms for shortest paths are used in your computer networks, where you have to find the best routing to from one source to another destination. Then backtracking algorithms, again, you've done an example of depth first search. When you traverse a graph and if you hit a dead end, you traverse back and you go to the next adjacent node. So if you recall your depth first search, that is actually backtracking. There are many other examples where you have backtracking. Let's say your chess placing, there's a problem of placing queens on a chessboard, four queens in a 4x4 chessboard, graph coloring problem, where we use backtracking if we hit a dead end or if we hit uh, a, a step where our conditions are not met. So we retract and we then go and try another approach to solve the problem. So similarly, a similar example is of another type of algorithm is branch and bound. So this is a way of solving a problem by looking at all the possibilities that are available and then exploring all the possibilities. So you branch means you see, okay, what happens if if you have to you are in a maze and you have to go from start to end. Let's say, what if I take this direction? What happens if you hit a dead end? Then you come back, say, okay, let's try option 2. So you try all the different branches, and then you see which one gives you a solution. The bound in this branch and bound algorithm, it tells, it is a kind of approach which we use where we know that this branch is not going to give us a solution, or because of some environmental factors we know that this will not lead to a solution, so we will bound or we'll cut off that branch and then move on to the next one without exploring this particular one. So all of these algorithms will be covered with a couple of examples each. Initially we'll do a couple only, and if we have time left then we'll cover extra examples of each type. Okay, so this is fr- from the presentation. I'll just try and explain some things to you. So, so uh, I'll give you a simple example of expressing your algorithm runtime in terms of a mathematical function. Okay, so okay, so these are different mathematical functions that you can that you we usually use to define the runtime analysis. If you remember, I told you the height of a binary tree is log n. N is the number of nodes. So if you have to search for a node, let's say in a binary tree, when we, so for example, in heaps, when we are doing insertions or deletions, we traverse the height of the tree. So how many steps required in insertion and deletion? It is equal to the number of levels or height of the tree. What is the height of the tree? Height of the tree is log n. So when you are deleting in a heap or you are inserting in a heap, you you have to go through log n steps. So basically that is the runtime of a heap. So inserting n elements in the heap will take n log n time. Deleting n elements in a heap will take n log n time. So if your n, for example, is 10, your n square is going to be 100, n cube is going to be 1000. What is log n? Let's say it is to the base 10. Log 10 to the base 10 is 1. What is n log n? It is 10 into 1. Okay. Let's say your n is 10 to the power 3. So what is n squared? 10 to the power 6. N cube is 10 to the power 9. What is log of 10 to the power 3? Log of 10 to the power 3. If you remember the formula, it is 3 log 10, which is 3 into 1. Okay. And then what is n log n? Your n log n is, your n is 10 to the power 3, and your log n is, in case of this, it is 3. Again, let's say 10 to the power 6. This is 10 to the power 12. This is 10 to the power 18. This is log of 10 to the power 6. It is 6 into 1. This is 10 to the power 6 into 6. Okay. So now if I tell you my program runs in n cube time. So what you have to do is you have to see if the input is 10, it takes me 1000, let's say, units of time to run my program. As my input increases, see it's the polynomial of degree 3. Every time my n, I have increased it from 10 to 10 to the power 3, it is 10 to the power 9. When it becomes 10 to the power 6, it is 10 to the power 18. Okay. So you see how the function grows, in the sense the mathematical function grows as your input grows. Okay. Now look at, if my program runs in log n time. If my input is 10, I take only 1 unit of time to run it. If my input is 10 to the power 3, see the comparison. 10 to the power 3 is 1000. For 1000 input, my log n function, my program running in log n time, takes only 3 units of time. And when it goes up to 10 to the power 6, it takes only 6 units of time. So when you look at an algorithm for sorting, where you see log n, if you remember your quick sort and merge sort, many of you have read it before. We'll see how it is n log n. The run time for merge sort is n log n, and the average case runtime for quick sort is n log n. Its worst time is n square. Okay, so merge sort and quick sort are supposed to be the best. Look at the last column. Merge sort and quick sort are supposed to be the best algorithms for sorting. Why? Because if you have to sort 10 elements, you see that it takes only 10 units of time. If you have to sort 1000 elements, it takes only 3000 units of time. If you compare it with n square runtime of bubble sort, it takes 10 to the power 6. So the difference is drastic, of the order of 10 to the power 3 between bubble sort and between merge sort, for example. Yes, obviously the algorithm is here, recursion is employed in case of merge sort. In case of bubble sort, it is a simple for loop, double for loop. But then you see the drastic difference in terms of the units of time, if all these numbers represent units of time. Okay. So whenever we do a runtime analysis, we look at we look at what we get in this column. Okay. The first one. What is the runtime? Is it n? Is it n square? Is it n cube? Is it log n? Is it n log n? Is it n square log n? It can be anything. Okay. And when you have to compare two algorithms, let's say one of them has log n runtime, another has n log n runtime, or one has n log n time, another has n square log n time. The best way to do it is to make a table like this and try with some values, let's say 10, 10 cube, 10, 6, 10 to the power 10, and see how the two functions grow in comparison, so that you are, for some functions you will see, let me see if I can give you an example. I'll rub this off. Mm. For some functions, what you will see is up to a particular point of time, it looks like one function or one mathematical equation is less than the other one. But as n increases, they just change the equation. Okay. When we talk of runtime analysis and we talk of these mathematical functions that we use to define how much time a program takes to run, we say this grows slow. The words that we use is, let's say, if you compare here bubble sort here and merge sort here, we say the bubble sort based as the input increases. For bubble sort, the function grows quickly in the sense the runtime taken, it grows kind of uh, not exactly exponentially, but then yes, it doubles, step from 10 to the power 6 to the 10 to the power 12. On the other hand, if you look at merge sort, sorry, it is n log n. Yeah. So if it's 10 to the power 12 here, it is 10 to the power 6 here. So it does not grow as drastically as merge sort grows. What grows? The runtime. The runtime in case of merge sort grows drastically when n is increased compared to merge sort. It does not grow as fast. So what does that mean? It doesn't grow as fast means it does not take as much time when the input size increases. So it is a better way of implementing your sorting problem. Okay. So just as an introduction to your this O of 1 or O of, let's say, n. So what does it mean? Okay, what is O? O is it's known as an asymptotic notation. Asymptotic notation. Okay. So what is it? It's nothing to be scared of. It is just a mathematical way of comparing two functions. Okay. Let's say if you have to compare n and n square. Okay, go. Sorry for the interruption. So if you have n and n square, if I ask you to compare them mathematically using logical operators, n is less than n square, obviously, right? Then, okay, let's compare n and log n. Okay, the log we will use in case of this uh, force, we use normally log to the base 2. Okay, not to the base 10, because many times we deal with divide and conquer type where you have numbers which are expressed in powers of 2, so we use log to the base 2. Okay, log to the base 2n. So I just write 2 here, log to the base 2n. Okay, so if n is let's say 2 to the power 4, what is log n? 2 to the power 4, it is 4. When n is 2, let's say it's only 2, what is log to the 2 to the base 2? It is 1. When n is it's 2 to the power 8, log n is 8. Okay, so which one is greater? N is greater than log n. Okay, so उसकी क्लास तो बोलो खाटो ये क्लास है. So when you compare these numbers, we are not comparing actual numbers, we are comparing n and n square are basically mathematical functions. You can write, let me clear this screen. You can write f of n equal to n square, g of n equal to n.
सही है ठोस होती तो टूट नहीं जाती ठोस होती तो टूट नहीं जाती
Yes, please, whoever is speaking, please mute your mic. Okay, so you have two mathematical functions, fn and gn, which are given like this. Okay, so you need to compare the two. How do you compare? You just compare the values. If n, let's say again, I'll write it here. this is your n, and this is your n square. If this is 2, this is 4. If this is 2 to the power 4, this is 2 to the power 8. If this is 2 to the power 10, this is 2 to the power 20. So obviously Gn is less than Fn. Okay. What if n is if n is 1, what is n square? N square is also 1, right? So we can also write Gn is less than or equal to Fn. Okay. This is what I'm doing is I'm comparing two functions. And what do I mean by comparing two functions? When we talk of functions, if you want to know whether one function is bigger doesn't mean it's mathematically, because you're comparing it with another function. We say Fn grows at a faster rate than Gn. Grows means when n has a value of 2, your Gn stays at 2, Fn is becomes 4. So when n becomes 2 to the power 4, Gn is only n, so it stays at 2 to the power 4, and Fn is 2 to the power 8. So if you see the values of Fn and Gn does not grow as faster than Fn, or you can say Fn grows faster than Gn. So we are comparing two functions, and this is how we can compare. So your asymptotic notation is nothing but a comparison of your functions. If your Gn is less than or equal to Fn, where Gn and Fn are both functions, for some uh, where n is greater than or equal to n0, it's a constant. So we write if your Gn is less than or equal to C into Fn for some constant C, and for n greater than or equal to n0, then we say that Gn is, or you can say is equal to O of Fn. So I'll give you a proper definition. Let's see if uh, uh, if you can see the screen, No, this is a little bit complicated at this stage. Okay, no, I'll give you hand notes on this one. Uh, let me go back to the whiteboard. Okay, so when you if you understand this simple concept that you can compare two mathematical functions, fn and gn, and you can understand for given values of n how the two functions grow with respect to each other. So when I say grow, it is like this. So okay, gn is less than, this is your fn. So this is not n and n square, obviously. These are some two functions, gn and fn. Okay, if you can see their graph, this is your n. Okay, and they are plotted with respect to increasing value of n, and this is n0. Okay, if you see before this value n0, you see gn is above, the graph of gn is above the graph of fn, right? But then if you see after n0, n0 is some value of n, gn constantly stays below fn. So beyond n0, you can safely say that gn is less than, or you can say even equal to fn. Or it can also be written as c into fn, some constant into fn. Okay, so the functions, the growth of the functions with respect to each other follows this graph, and in this graph you can see that beyond a certain point n0, gn always stays less than fn. So we say that gn is O of fn. This is another way of writing gn is less than or equal to fn. This is called big O notation. Just a way, mathematical way of comparing two functions. Why we have to compare two functions? Because when we do the runtime analysis of our programs, we say, oh, this program takes n units of time, this another program takes n square units of time, my merge sort takes n log n units of time. What are this n square, n log n? These are all mathematical functions. So when you have to compare n with n square with n log n, or n with n log n, you need to tell me which one takes more time based on the input. You do not check it for, let's say, input 1 or 2. You check it, plot it for a series of values, and when you plot and you get a graph like this here, then you can safely tell me, oh, you know, this is the pattern these two functions follow. So I can safely say gn does not grow as fast as fn, or you can say fn growth rate of fn is more than gn. What is growth rate? With respect to input size n, the growth is follows this pattern, and this pattern is what we are defining by big O. Okay, so if, for example, so if gn abhi tak it was less than fn, if it's the other way around, gn is greater than fn, that means when you plot the graph something like this, this is gn now, and this is fn, and this, if they follow a standard pattern beyond n0, this is your n. So we say the notation we use for greater than or equal to is known as omega. I'll give you the formal definitions. This is called the omega notation. To tell if some function is greater than or equal to another function, fn, we use this notation. If it's less than or equal to, then we use big O notation. So first is big O. These are all known as asymptotic notations. This is your second one. This is omega. If I rub this equal to, please mute your mic. Please mute your mic.
चिकन बिरयानी हाफ हो सकती है सिंगल अच्छा ये 170 कोई नहीं ठीक है
Can you mute your mic, whoever is talking?
हाँ
Okay, so if I remove this, I had a greater than or equal to. If I remove this equal to sign, I use what is known as, this is called small omega. And similarly, if Gn is less than or equal to Fn, we said Gn is O of Fn. This is the big O. If Gn is less than Fn, then we say Gn is small o of Fn.
भैया एक बिरयानी भी देना
बिरयानी बाद में खाना, पहले पढ़ तो लो. पढ़ो मत तो म्यूट कर लो, बाकी सबको भूख लगेगी आपके ये सुन के. जो भी बात कर रहा है, can't figure out, I am on the whiteboard. Okay, so if this is the equation between your functions, then it is Gn is small. This is called small o. This is your big O. Shh.
I was using your phone.
Okay, so you have big O, small O, and you
भैया
have
मैम के लिए भी बिरयानी देना
okay, cool. So big O, small O, big omega and small omega, and then you have something else. If you have a situation,
भैया बोला ना मैम के लिए भी एक बिरयानी
if your Gn and Fn are equal, so equal doesn't mean, in case of function growth, it doesn't mean that let's say this is n and this is also n. It can mean this is 3n and this is 5n. Okay, we'll see in some examples later. So for now, if your two functions grow at the same rate, then we use the notation which is known as theta. So if two functions grow at the same rate, then they are related to each other using this asymptotic notation called theta. For example, if you have 2n square, n square, 5n square, and if your n is, let's say 10 to the power, it's 10. So this becomes 200. This becomes 100. This becomes 500. So when it's 10 to the power 10, you have 2 into 10 to the power 20. You have 10 to the power 20. You have 5 into 10 to the power 20. So when you reach this stage where for higher values of n, what is more predominant? 2 into 10 raised per 20 may, this is more predominant, right? So when we are talking of two functions related to each other by the asymptotic notation theta, it's written like this, then we do not mean exactly they are growing they are growing at the same stage. It doesn't mean in the graph they are overlapping like this. It means that they are growing at the same rate. You'll see when you see the definition, we'll do the formal definitions in the next class. They do not grow like this. It's not they're overlapping two functions, but they are growing at the same rate. We'll see that in the formal definition. So because you see the majority of the main part or the main portion of time is spent in this 10 to the power 20, this 5 and 2 doesn't matter, then we can safely say all these functions, they are theta of each other. Okay. So you have in asymptotic notations, you have big O, which is denoted like this. Then you have small o, which is like this. Then you have omega, which is denoted like this. Then you can have small omega, which is denoted like this. Then you have theta, which is like this. If you are comparing two numbers, I can, just for you to remember, a is less than or equal to b. This means a is less than b. This means a is greater than or equal to b. A is greater than b. And this means a is equal to b. But it's not, we're not comparing two numbers here. So it's not exactly like this. But for you to remember, big O means this. Small o means this. This is omega, small omega, and theta. Okay. So we'll do the formal definitions in the next class. So for now, just remember when you have to compare two mathematical functions, you are comparing their growth rates. Growth rates with respect to input. As the input grows, how does your function grow? How does it behave? How does its curve go? How does its curve behave with respect to the curve of the other function that you're growing? If they maintain a constant difference of one being below the other, or other being above the other one, or one function being in between two functions, then we denote them, we relate these two functions or equate these two functions using these notations. Okay, so these are your asymptotic notations. So we'll do the formal definitions of these and the recurrence relation solving in the next class. I think we still have half an hour, but I guess for introduction this is all right. And लोगों को already भूख लग रही है and people are drawing and doodling around. So just a second, let me stop this sharing. If you have any questions, you can raise your hand. We can have 5-10 minutes for that. Then you can raise your hands. I can unmute you. Nobody has any questions? I have turned off mic permission for everybody, but I don't know. I have to change the settings again. Okay, anybody having any questions? Okay, if you have any feedbacks, it's difficult to draw on this board. I tried using some homemade kind of device to write, but I think my finger is smoother on this whiteboard. I can't write much in one screen. There's a lot of mathematics I need to do in the next class. So maybe I'll use some existing slides for showing you some examples and do a couple on the whiteboard. Because I don't think I can write, I don't know how properly it's visible to you. I have to write. Writing mathematics is a bit difficult for solving the recurrence, but I'll try. First, I'll see if I can show you some examples which are already solved, and then we can do small ones ourselves. So if you have any feedbacks or uh, anything, I do not have my own notes with me right now. They are with some other person, but I am not planning to do handwritten notes. Uh, in case I find my own old notes, I will send it to you. I will also send you PDFs which are related to the class notes. Maybe most of you do not have books. If I have any ebook, I'll send it to you. But I'll try and I'll I'll send you notes as per the lectures, and I'll also give you this presentation. It doesn't have much information, but just an outline. I'll email it to you. Uh, Whenever there's a presentation, I'll email it to you. Whenever I use some PDF to teach along with the whiteboard, you can use that. I'm also recording these Zoom classes online. So that if somebody wants, we can share those as well. Amandeep, are you there?
Yes, ma'am.
Yeah,
Yes,
I
ma'am.
need you to take attendance. From what I
Yes, ma'am.
know, the rules or evaluation might change for this semester because now the classes are going to be regularly online and they have asked us to maintain attendance in classes. So uh, it might be that you might be given some marks for attendance. It is just an assumption on my part, but then I just wanted to inform you ahead of time so that for end May you do not lose marks. So attending this class is very easy. You can just log in and just not listen to anything. That is not my concern. But if you're worried about your marks for attendance, then you should at least log in to see what is happening in class. I'll also create a Google Classroom so that I can share whatever PDFs and notes I have or links online with you there. Okay. So Amandeep, can you take a screenshot
Yes,
of
ma'am.
all the participants and send it to
Oh,
me?
okay, ma'am. Okay, ma'am.
Okay, so that I can
Yes,
maintain
ma'am.
attendance. Uh, I understand some people get logged out because of network issues. So you can let me know if that issue is there while you are attending the class. I will not entertain anything after that. So if you're having any issues not being able to connect or stay connected, you can just message me privately on Zoom that you are having issues so that I can mark your attendance in case you're not in the list. Okay. So if you're done, Amandeep, let us know so that
Yes, ma'am.
everybody can
Ma'am, I
leave
have taken the screenshots.
for all the participants, right?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
Okay, yeah, you email it to me.
Okay, ma'am.
Okay, I think that's it for today. Maybe my Ruhi ma'am will take my class tomorrow. I'll inform Amandeep and he'll let you know. Okay, because I took her class and half of my class today, so she might take 2 classes tomorrow. So give your feedbacks if you have anything that you want me to change in the way. This is it's very weird to talk to the screen like this without having any student in front of you. But then uh, mm, I'm trying my best. If you have want anything changed or any feedbacks which I can accommodate, please let me know. Okay, through your CR. All right. Thank you. You can leave.